Number 3 is very crucial, and in Volga language, it is usually called trigonometric, a triangular inequality, which I usually don't use. I just say it's third axiom for metric spaces. It has lots of relevance in geometry, the third axiom. And then we go to the typical examples of metric spaces. We all know you should have really verified all these when you're doing linear algebra and analytic geometry. Euclidean spaces. When we say Euclidean spaces, we mean that it is a vector space over R with an inner product defined. Inner product satisfies its own axiom. And that gives you a metric space, very typical one. For example, Euclidean plane is where Euclid worked on using compass and ruler. So it's all there. And geometric spaces. Geometric spaces are, this is an abbreviation of spaces with constant curvature. So there are only three there. Actually, typically there are only three: Euclidean spaces, Riemann spaces, and hyperbolic spaces. Hyperbolic spaces has in differential geometry sense, it has a constant negative curvature everywhere. Riemann spaces are the typical two-dimensional one is the sphere. Everywhere it's a constant positive curvature. And Euclidean curvature is zero. These are, and also there's a more modern, it is modern and not modern, graphs. For those who did graph theory already, graphs, particularly my graphs in here are lots of other things as well, but undirected, finite, connected, simple graphs, which is graph theorist graphs. They are easily to be verified that they are metric spaces with their path metric. Then the next one. These are subsets of Euclidean plane. These are all metric spaces. These three are metric spaces. Any line segment, it has a distance between these points and which you can verify that all three axioms are satisfied. Even that rectangle perimeter and the unit circle, let us say it is unit. And go forward. And even in Euclidean spaces, Rn, you have to really know that Euclidean space is a vector space over R, over real numbers. You cannot really talk about Euclidean spaces over complex numbers, which will give you a unitary space and spaces, and over pure or any other field, which will not necessarily give you a Euclidean space. Euclidean space is exclusively over the field of real numbers with inner product defined, inner product axioms. And then for Euclidean spaces, we give three examples for n equal to 2, which is the Euclidean plane. These three functions can be easily verified to be distance functions, which is, you need to do it as an exercise. Distance functions, it satisfies all the three axioms, which gives for each different distance function, the Euclidean plane or any Euclidean space gives you a different metric space. And another typical example which we do it in homology all the time is the discrete metric. Discrete metric regards any two distinct points, any 2 points which are different, to have distance 1. And you don't need to say same point have distance 0 to itself, because that was already postulated as an axiom 1. So this gives a space called discrete metric space, and it gives us examples from many statements which were stated in a silly way by not knowing it. Continue. And now, in this course, we're going to preserve the symbol chi, the function chi, to be the characteristic function or indicator function. So in this case, in the case of discrete distance, it indicates whether x not equal to y is true or not. If it is true, it's 1. If it is not true, then it's 0. Not true means x and y are the same. And we keep this function for the whole course, and you can use it when you're writing anything. Next. Now, this is one of the things good about metric spaces are bad in general. And it is good about, this is just like topological spaces. Any subset can be made into a subspace using the metric of the ambient space. That is very easy to be verified, this proposition 1. And we call that metric induced metric. If the subset has its own metric, which is different from the ambient metric, distance function of the ambient space, then we call it is the intrinsic metric. And we're going to rigorously define that word, intrinsic, in a few slides away. Now, we define several things. These are coming, because one of them already appeared here. The sphere, n-dimensional sphere, is a subset of geometric subset of n plus 1 dimensional Euclidean space, which satisfies your familiar equation for a sphere. Sum of components, sum of the squares of components is 1, or constant. And after doing that, we can easily define using inequalities open balls and closed balls. Because these are not completely used in our course, but it is going to be used once for the topology of metric space. And in this whole course, we assume algebra and topology, especially linear algebra. Linear algebra, if you are not, if you forgot some of them, I will remind you when it comes, especially linear algebra. Continue. We need to take rest in between or continue? Continue, and then please demand me when it goes to 90 minutes.
You feel tired or something?
No. When I work, I don't feel tired. Only when I rest, I feel tired. So the Bn plus 1 is called the open ball of dimension n. And it, with a bar on top is a closed ball of dimension n, which is the union of the open ball and the sphere. Sphere is the boundary. So we now address the topology of the metric space. As soon as this is usually done in topology courses, topology should be done rigorously in our school here. This is what I was suggesting to DG. Let me write in alphabetical orders. Algebra, analysis, geometry. This is every one of these 2 parts. And then we have topology, combinatorics. Backbone of mathematics. And of course, application is very important, and we should respect real applications. But without these 5, the mathematics school cannot survive. So this is the lifeline, so we have to really do this solidly and simply. So we are now going to consider the topology of a metric space. As soon as a distance function is present, we can have the definition of using only distance. We can have the definition of open ball, and we can actually define open set with it. So an open set is very easy to define. Open set is a set in which every point has an open ball containing it, which is completely contained in the set. So that set is, for every point of it, it is satisfied. The set itself is called open set. And closed set is usually complement of an open set in the whole space. And then, Lisa, you can go forward now, because we're now passing through this fast. It seems everybody knows about this. So at every point, we can actually define a neighborhood. Any open set containing a point is called a neighborhood. So we can keep the basis of a topology, therefore the topology is determined. From that on. Of course, it was done the other way around in topology courses, isn't it? First topology, then you try to address the basis. And all of these are in general metric spaces. These are geometric sets. Because we use only distances. Look at that. P sub R is the open wall of radius R centered at A in metric space X, any metric space, including graph, including all those geometric spaces. And then this is defined using only the distance function rho. That fits our topic because our topic is geometric sets in metric space. We only need distance. And similarly, the closed ball scale, these are all defined using distance of it. Continue. And neighborhood, everything is done. So now we can define sequences. There are many people in the world now doing sequences ungeneralized or varied convergence about it. You should really check some of the literature, and I have seen some activities even around in South Asia. And they're very interesting and just beginning, which means you can do questions not too difficult way. Something is beginning like this subject is a beginning subject actually, although it has roots in many important fields. You will see when we continue. This means that we can do some question without too much suffering. I don't want people to do things and suffer. I want people to do things and really like it and enjoy it. You see. This is what the mathematics is all about. It's a life and it has. So now, any mapping from a subset of natural numbers to a metric space is called the sequence. The natural numbers in the domain simply indexes the value in our usual writing. So it's x sub n is actually f of n. So such a mapping is called the sequence, and if a subset is finite, it could be just 2, 5, 25, 70, and so on. If subset is finite, then we call the sequence finite sequence. Otherwise, it is infinite sequence. It doesn't necessarily mean that it has to have all different values. All ones, starting 1, 1, 1, 1, constant sequence is infinite sequence. Or if it stops somewhere, it's finite sequence. Continue. And the sequence is called convergent. If the convergence, this is from calculus. Only that we now have our sequence x sub n in metric space X. And the other epsilon delta is epsilon n sub naught is natural number. And epsilon is a positive real number. Nothing changed except our sequence comes out from a metric space and we have a distance which is compared to the epsilon. So this is called this is the definition of a convergent sequence. The definition of a Cauchy sequence is similarly defined, only that here we use two indices instead of one fixed number in the arguments of the distance function. In that first definition, A is an element of the metric space, it's a point. And in the second one, both xn and xm and xn are points in our sequence. So here, Cauchy sequence, one thing about Cauchy sequence is that it is only making use of the sequence itself instead of referring to another point outside it. It could be outside to be inside another point. So this is the definition of a Cauchy sequence. It is actually a weaker definition. And this gives us that what is the relation between a sequence which is convergent and a sequence which is Cauchy? If a sequence is convergent, is it Cauchy?
No.
Yes, and then it's the next proposition. And if a sequence is Cauchy, is it convergent?
Yes.
Necessarily? No.
No necessarily.
general space it is not. And if that condition is satisfied, the proposition is proved now. So we easily, this is the theorem 2. If even in metric spaces, if a sequence has a limit, then the limit is unique. That proof is exactly the same as the beginning analysis. And every convergent sequence is in a metric space Cauchy sequence, as you just said. This is true. The main thing is that its converse is not necessarily true, which makes the concept of a complete metric space important. So definition of complete metric space. Complete metric space is a metric space in which every Cauchy sequence is convergent. That is one way of proving that the field of real numbers is complete. It's a complete Archimedean ordered field. One way is from Cauchy angle. You know that if you did analysis very well, there are at least seven different angles, equivalent statements which you can prove, which you relate to the completeness axiom, right? Have you ever tried? When we were students, we were very fond of it, when we were your age. There are seven different statements, theorems actually, which are equivalent to the completeness axiom. The completeness axiom nowadays usually stated in English text is that every non-empty set of real numbers bounded above or below must have a smallest upper bound, must have a supreme. This is called the completeness axiom, and it is, because of the English text, it is stated in the most simplest way. Of course, there are seven others. One is Cauchy, is completeness. So this is one of them. Even for metric spaces, you can see that Euclidean spaces are all complete. Starting from the R is complete, and then everything else follows from that. Okay, limit point. The limit is called the limit point. In this case, it may or may not belong to the metric space. We're going forward. Now here is the definition which is from discrete mathematics. We want to know what we want to talk about covers and decomposition of partitions. So what is a cover? Cover is a set of subsets. Or set. Cover is the X will set, and then AI is all subset. If the union of all these subsets contain the whole set, it is naturally, you should really know that in discrete mathematics we know that the union of any subsets is actually a subset. But it contains means that the set itself is also contained in the union. That you need to, only that part you need to prove when you want to verify. If these two conditions are satisfied, then we call this set of subsets to be a cover. And cover is very important. Each mathematical subject, there's something about, some papers are published about covers. And if the cover satisfies one more condition, that different subsets are, distinct subsets are disjoint, then we call it a partition. Very important, because we know that from discrete mathematics that three things are equivalent. One is equivalent, let X be any set, and R be any equivalence relation on X. Then this equivalence relation partitions the set into equivalent classes. Number one statement. Number two statement is that if you have a partition of a set into subsets, then there is a mapping from this set to some other set, so that each part is defined by each part defined images. Number three statement, if you have any mapping from X to Y, let X and Y be sets. If you have any mapping from X to Y, then this mapping defines an equivalence relation on X. The second two statements are not difficult to prove. The main difficulty, non-trivial part is the proof of the first statement. That is what we do in discrete mathematics, and forget about the two others. And mathematicians are expected to use all three of them interchangeably, right? According to their own convenience. So this is where we come partition, and if the partition is there, there must be an equivalence relation, and there must be a mapping. So it's all up to you to use. Continue. Now we define what is meant by bounded and totally bounded sets. Bounded sets and matrix spaces. Because we have a distance function. So we use the distance function to define these. Boundedness means that between any 2 points of the set, the distance is bounded by some fixed positive number. If the set itself is the whole space, we call the space bounded. Totally bounded means that there exists a fixed positive number so that every point, so that the whole space is covered by finitely many balls of that radius. You can actually even possibly use open balls. So totally bounded is stronger condition than boundedness, because you can easily see from there even that if a set is a subset of a metric space is totally bounded, then it is bounded because you have finitely many balls of the same radius. Their total longest distance in the set is at most finitely many times that same arc. So that is the next statement which we prove. The proof is already set. The set is totally bounded, then it is bounded. So the proof is set already because there is a finitely many balls of the fixed radius. In this one, this is done. Okay, compact. Compact is the topological definition of compactness, because for any given, here we are not saying that there exists a finite fixed number so that it is covered by finitely many balls. We are not saying that. It is very different. For any given open cover of the set, you can always, this is open cover, always there exists a finite subcover. You can choose finitely many of them to cover. That is the definition of compactness. The best one of them. Of course, compactness also has 6, 7 equivalent definitions. You should check out all those really good analysis and topology books. So this is the definition of compactness we are using for any open cover. Any open cover of the set, it has a finite subcover which covers the whole set. Because some people are confused in this when they're being questioned. For example, if you have a topological space X, X itself is open by agreement, not by seduction. Empty set and X themselves are open as the first action. And then you cover this X by itself is covered, already finite cover with one. It doesn't mean that. It means that if the same set, if you are given any cover, any other cover, you still find a finite subcover you can find from it. So this might have a cover which is very high cardinality, high infinite cardinality, from which you can choose, if it is compact, then you can choose a finite cover out of it. That is our definition, and continue. This is the next slide. Yes, this is our theorem. The theorem is that the metric space is compact. Also, the topological space is compact. It's already done very nicely in topology. The metric space is compact if it is complete and totally bounded. This is our statement. This actually follows from the topological excessively sufficient condition for a subset of the topological space to be compact. It follows, but let us look at the definition, the proof. Here we're using something called sequentially compact. Sequentially compact means that if you haven't done topology yet, maybe most of you have done already. Sequentially compact means that if you take any sequence, any infinite sequence, it must always have a convergent subsequence, which is one of Weierstrass three theorems in analysis. In analysis, remember Weierstrass proves three theorems. Number one theorem is that every convergent sequence is bounded, right? Every convergent sequence of real numbers is bounded. That was the first Weierstrass theorem. And then immediately he asked whether converse is true. Is every bounded sequence convergent? No, and immediately you give very simple examples which is not.
Yes.
So after that he asked, what other conditions we can add onto the convergence so that we have boundaries? Or what other conditions we can add on the boundaries so that we can get convergence? So the second Weierstrass theorem in analysis says that if you have a monotonously increasing sequence bounded from above, then it is convergent.
Yes.
Or monotonously decreasing bounded below convergent. This was the second Weierstrass theorem. The third Weierstrass theorem said that every infinite sequence on a closed interval has a convergent subsequence. This Weierstrass really made the analysis very good. So this is not one of them. So using the sequential boundaries, so we're going to prove only the sequential boundaries to be equivalent to being compact. Let's see this. Which part are we? So let X be a metric space with this function rho. If X is compact, then definitely it is sequentially compact, which is what which is exactly the same state of the Weierstrass theorem. Therefore, it is complete. One side of this is, if I know you, one side is easy, the other side is the two involved. So let us suppose that X is a compact space. So by definition, any cover of X by balls of radius epsilon, any real number, positive real number, must contain a finite subcover. And